Hello everyone, it's Chuck back again with another episode of the Refrigerant Checkup. Today I want to share a conversation I had recently with one of our engineers, Andrew Pansulla, about a tool you may find very useful. It's what we call the Chemours Refrigerant Expert. It's available online at no charge, but allows you to do a variety of cycle calculations and property information to really understand what's going on in a system. You can select various refrigerants, various inputs, and give you some useful information. So I'm going to show a little conversation I had with Andrew, and he kind of describes the tool very briefly, but gives an example of how it may be used when considering something like temperature glide, something we're all interested with, understanding how it can impact system performance, energy capacity as we go from refrigerant to refrigerant or system to system. So if you have any questions, we'll put the contact information out at the bottom, or if you'd like to get a hold of the tool, we'll show you how to do that. It's a pretty simple download, but let's get Andrew on here, and so let's roll the tape. Okay, so we're here with Andrew Pansulla, one of our engineers. Andrew is going to introduce us and show us around a little bit the Chemours Refrigerant Expert Tool and some of the calculations and things it can do. So Andrew, I'll turn it over to you. Take it away.
Great. Thank you, and hello, everybody. I'm going to share my screen to get the tool open here. And when you're using the Chemours Refrigerant Expert, the first screen that you will see is this one. And all you have to do is click OK, and then yes. And then you will have a selection of 4 different options for which cycle you want to run. So these cycles are the standard vapor compression cycle, a vapor compression cycle with the suction liquid line internal heat exchanger, a cascade type architecture, or a single stage heat pump cycle. To walk through the tool today, we are going to go over the standard vapor compression cycle. So as you can see, there are a number of different options and inputs that you can do to do any type of evaluation that you're looking at for any refrigerant. Any of the words in bold can be changed by the end user. So your condensation temperature, your evaporation temperature, subcools, superheat, pressure loss, or your isentropic and volumetric efficiencies are all going to be changed. And then the theoretical displacement and the capacity are connected based on what refrigerant you're working with. So that means if you were to change this to, say, 8,000, you will see that the capacity will change based on using 134A. And if you were to change this to, say, 400,000, the theoretical displacement then changes based on this capacity and these conditions for 134A. So those are the different inputs that you can do on this tool. And then there's a number of different refrigerants that are in there. So you can do pure component refrigerants like 134A or R22. There's some of the historical HFCs that you see in there, that you see in the industry, such as 410A, 407A, 404A, or you can even evaluate some of the newer refrigerants that are out in the marketplace, such as R449A, 513A, and 452A.
Hey Andrew, the pressure enthalpy diagram up there in the upper left, that is updated based on the inputs of temperatures, evaporator, condenser temperatures, and the particular refrigerant, right? Anytime you change those inputs, that will update that pH diagram.
That's correct. So for the example of changing the temperatures, you can see here right now we're doing a condensation temperature of 104 F. If I were to increase this, you can see on the pH diagram on the left that the cycle that you're running, the box changes. So if you were to go up to a hotter temperature, say you're somewhere really, really hot where it's 130 F out, you can see that that pressure increased and it was reflected in the pH diagram. And you can do it again with the evaporator. And it's a really good tool to try to visualize what's happening in a system for a given set of conditions. So what happens as you're condensation temperature increases, or what happens if I need to run in low temperature refrigeration versus medium temperature refrigeration. So the tool is very powerful in giving you both the visual and also the computational results of those changes. And then, as you mentioned, you can also do different types of refrigerants. So you can see right now we selected 134A, but if we were to go to, say, 449A, you can see that the header up here has changed from 134A to 449A, and now based on these conditions, this is the cycle that would be operating. So other inputs in the tool also include a properties tab. So when selecting properties, there's different points in the cycles. So you have your saturated vapor. They're all listed right here. So you have the exit of the evaporator, the input to the compressor, the exit of the compressor, the input to the TXV, and exiting the TXV. And you can get the temperature, pressure, enthalpy, entropy, volumetric density, and the quality entering the evaporator for any condition that you would need to run. The other piece of calculations that can be used with this tool or with line sizing. So based on the different conditions that you're running, you can run different line sizing scenarios with the tool for any refrigerant that you're working with. So you can input things like, say, the total pressure drop that you're trying to do. So if you wanted 2F pressure drop for 100 feet of lines, you can input that and it will show you a recommended inside diameter and give you the velocity of the refrigerant going through the pipes for the conditions that you're looking at. So in that regard, it's a very powerful tool because it gives you the chance to really evaluate what you're doing with each refrigerant to see what the most optimized conditions are. So speaking of optimization, I think there's another important point to bring up about not only rating refrigerants for performance, but really just working with some of the newer refrigerants, and that's with temperature glide. So temperature glide is something that's becoming much more commonplace in the industry just because refrigerants, pure component refrigerants like R22, or even refrigerants with small temperature glide, 404A, 410A, for example, are really starting to be phased out or phased down in the industry. And a lot of the refrigerants that can match the performance of those fluids will have some degree of temperature glide. So what is temperature glide? Temperature glide is when you are either boiling or condensing a refrigerant mixture. If you had a pure component refrigerant, so let's say, for example, you had 134A, the temperature at which that phase change happens from either a liquid to a vapor or a vapor to a liquid is the same across the evaporation or condensation. Refrigerant blends, just because of the different properties when they're mixed together, such as boiling point, or even really on a chemical level, the interaction parameters between the different molecules, it causes the boiling or condensation phenomena to have some slight differences from a pure component. The main one being that the temperature as you're boiling or condensating is constantly changing. So for refrigerants that are used in the field, such as R449A, what this means is that as you were to go from a liquid to a vapor or a vapor to a liquid, you can see in some cases 7 to 10 degrees of difference without any superheat or subcooling from the evaporation or condensation. So how do you account for that and why is it important? You could see here for the evaporation temperature. So I'm going to move this up to, we'll do 20. So let's say you were trying to optimize a medium temperature cooler that you needed to run at a coil of 20F. So these evaporation and condensation temperatures are dew points. So if you're running a 20F dew point, your mean temperature is going to be 17F. So, and you could see if you were, as you change this, so say you're at 23F, your mean temperature is 19.9F. Or if you were to go lower, say to 17F, your mean temperature is 14F. Regardless of what you change your evaporating temperature to, the mean temperature or the actual coil temperature is always a couple degrees cooler in the evaporator than the point you're specifying if you're using a dew point. So why is that important? If you were to take a fixed theoretical displacement, which would require that would be in like a retrofit scenario, you could see as you change the evaporating temperature, the capacity changes. So at a 20F dew point or a mean temperature of 17F for this theoretical displacement, your capacity is 409,000 roughly. So what happens if you make your mean temperature 20F, right? That's the coil temperature we're trying to hit. So if you were to bump this up about 3 degrees, so the mean temperature is 19.9 F, your refrigerated capacity increases to 436,000. So that's one of the things that we really try to make sure is out in the industry, is this information that optimizing for refrigerants with temperature glide is something that's new, and you can get different performance based on how you're optimizing these fluids. The other important thing, so that's capacity, but if you were to go here back to 20, your EER or your energy efficiency ratio goes from 6.89 to 7.19. So if you needed to run a 20F coil and you can hit a 20F coil with a 23F dew point, from an optimization standpoint, it really would be a strong benefit to the system. The condensation side, it's a little bit of a different story from a thermodynamic perspective. So I'm going to bump this down to 100. You could see here in this case at 100 degrees, condensation temperature and a theoretical displacement of 7,000, your refrigerated capacity is 494 and your mean temperature is 95. So what happens as you bump up the temperature, your refrigerated capacity actually is going to slightly decrease. But this is the thermodynamic side of it. What also is happening is the heat transfer side of things. What you see when you have a condensation temperature change from, say, if you wanted to run a 100-degree dew point or a 105-degree dew point, even though that dew point has a lower refrigerated capacity, it has a greater delta T across the condenser. So because of that, you can get greater condensing capacities when sizing condensing units, when sizing based on the mean temperature versus the dew point. So those are a couple examples using CRE of how you can play with Glide. It's really a tool that I definitely recommend just picking a refrigerant and trying out different numbers and seeing how those numbers change the system performance, because I think it can lead to a really great understanding of all those new refrigerants that are entering the marketplace.
Yeah, I think a couple key points, Andrew, and I think you mentioned these. One is it's really most appropriate when you're trying to compare things to use a midpoint or average coil temperature, both in the condenser and the evaporator. But things get rated according to industry standards at dew point. And when you're talking pure fluids, it's not that big a deal. But when you get into things with some glide and maybe a little more glide, it becomes more and more important to understand exactly what you're comparing. So you don't have to run it quite as, you may penalize yourself unnecessarily by running it extra cold, your evaporator, when you really don't have to. If you could bump it up and adjust for that glide, get better capacity, better energy efficiency. Did I kind of summarize that correctly?
Yes, I think you hit the nail right on the head there.
Okay. Um, Obviously, a very powerful tool, and how can people get it? Right, it's free of charge.
Yes, the tool is free of charge. It's available right on our website. All you would have to do is search for Chemours Refrigerant Expert, and you'll be able to download the tool and start working with it.
Great. Well, thanks for that explanation. I think you packed a lot of information into a few brief minutes here. I'm sure there's a lot of other stuff the tool can do, and maybe we'll get you back on here at a future date to talk about some of the other things and experience you've had using it and how it's helped customers understand what's going on, especially as they're looking at new environmentally friendly refrigerants. So appreciate your time, and we'll be talking to you soon. Thanks, Andrew.
Great. Thank you.